Hi and Assalamualaikum everyone. So today I would like to share and deliver the second part of chapter number 6, Support Vector Machine SVM for our course Artificial Intelligence. So in this class basically we will talk about some introduction of what we did cover in part number 1 SVM, and then we will talk about the linear support vector machine. Started with the hyperplane, margin, support vectors, and then we will identify the scenario of the right choices of hyperplane. Scenario number 1 jumps into scenario number 2, then goes to scenario number 3, and up to 5. And then we will talk about what is the type of data that we have so far. And we'll show you guys some examples of support vector machine, and we will jump to the nonlinear support vector machine, following by kernel, and at the end of this particular chapter 6, we will discuss about the multi-class of SVM, including OVA and OVO, right? So to begin with, basically, I would like to introduce some important or crucial point for support vector machine. In this particular class, basically, I think we had heard about hyperplane, support vectors, and margin basically in part 1. So here, support vector machine is a supervised machine learning algorithm whereby the support vector machine is more or less doing good things in classification, and SVR, on the other hand, is support vector regression, is doing a good job in regression purposes. So this is the things that being a part of SVM for regression approaches. So now in this class, we will talk about SVM, not SVR. So SVM are commonly used in classification problems. So whereby we had discussed before in our previous class, when we have a case of cat and dog. So remember the things that we have cat and dog. So basically cat is a class number 1 while the dog is the class number 2. So in that particular class, basically we would like to see that the image has been given considering as a new unseen data will be classified very well or not well based on the classification that we have. And SVM here are based on the idea of finding the hyperplane. So remember in the part 1 we did discuss about this hyperplane. What is hyperplane? That best divide the dataset into 2 classes as shown in the image on the right hand side. So basically the hyperplane is a single line which separated the class 1, we might say the blue class, and class 2 in the left hand corner is considered as class green, right? Okay, so if SVM is discriminate classifier formally defined by separating the hyperplane. So whereby, as we mentioned earlier, we crucially targeting to how to get the idea of plotting the hyperplane in the data that we have in our hand. So in other words, given the label training data supervised in perspective of supervised learning, the algorithm outputs an optimal. So right here we have optimal hyperplane. So whereby the final target for us in SVM is basically to find the optimal hyperplane, which categorize the new example, or what we always call in our previous class as unseen data, very well. Is or alias we can say that the model could generalize the unseen data or new data that has been injected in any system that we have through our models. So in 2-dimensional space, this hyperplane is a line dividing the plane in 2 parts where each class lay in either side. So this is the one. So imagine that hyperplane is a green color of the line over here. So any point in the left of this particular line considered as black circle class, and on the right falls into the blue squares class. So this line is basically separated 2 classes that what basically SVM, support vector machine, does in the whole process. It finds out that hyperplane in multi-dimensional space that separate this class. So basically, this particular hyperplane will separate all the data. Right. So to discuss the support vector machine here, so basically here in this course, I divide the SVM into two sections. So one is linear SVM and the other one is non-linear SVM. So basically the first part will be talking all the thing which related to the linear SVM, and after that we slowly go into the non-linear SVM, which might be talking about the kernel trick or kernel perspective of separating data in high dimensional of data that we have, which is kind difficult to the linear SVM approaches, right? Okay, so first thing first, in SVM, the hyperplane is very crucial. So hyperplane is a line in the left figure that we can see over here, that linear separate and classify a set of data. So in this left figure, so we can say that this could be hyperplane, this could be hyperplane 2, and this could be hyperplane 2. But here, as to define only one of hyperplane, this is basically the line reflected to the nearest data, green data to the hyperplane, whereby the nearest data to the hyperplane, we call it support vector for green, while this particular line is presenting the line which located the closest data for the blue data point, which also called as support vectors in the other hand of blue data, and this would be the green data. So this is what the range, or the distance between the two lines, is basically what we call margin. So afterward we might discuss about the margin deeply. So it can be a line right figure. So on the right hand side, basically we can sketch the hyperplane in several choices, or several angles that we could. So example, this is the first one that we did discuss in the left hand side. So we have the second one, we have the third one, or we might add some more. So basically those particular line is basically try to find the most suitable to separate the blue data point and the green data point in the context of SVM. So, but here we need to remember that the goal in the SVM is to choose a hyperplane that with the greatest possible margin. So right, so the great possible margin between hyperplane and any points means that the support vectors and the selected line will be having the most furthest or greatest margin, or the widest margin that we have, and or that we could have in the selection of several hyperplane. So if the line that maximizes the distance between the class is identified, that the probability to generalize well to unseen data is increased. So this is very close enough to what we did discuss last week, the moment that we did discuss about generalization, remember? So in order to generalize the model, so basically we need to have add what we call it lambda and the penalized component in loss function. Remember the one that we did discuss last week. So here, in order to have to make sure that this hyperplane could generalize all unseen data or all the new data, so basically we need to ensure that the margin to the support vector machines is far enough, not close enough. Okay, so this is the example of hyperplane that we have. So example, we just focus on the black hyperplane over here. So we have kind of a large margin between the blue data points and the red triangular data points. So compared to the gray shaded line, so basically we have a small kind of margin over here, and also we have the small margin for the closest data points, or what you call it support vector over here. So compared to the black solid line to the gray shaded line. So we can see that here the black is better than the gray shaded lines in terms of hyperplane itself and according to the margin. So right, so just mention about margin, and then I will explain about margin is a crucial concept in support vector machine that refers to the distance, right? Distance between the decision boundary, alias we call here hyperplane, and the closest data point. So meaning the closest data point for each particular class is either green or red, for instance, in this particular slide. Okay, so first of all, we call the largest width margin that we have, that we could find here, is maximum or hard margin that we call it. The hyperplane is placed in such a way that this margin is as wide as possible. So meaning that we could find the largest or the widest possible margin that we could from the selected hyperplane that we have in the SVM approach. So that would be called as maximum or hard margin. So on the other way around, basically we have soft margin in the case that where perfect separation is not possible. In example, noisy and overlapping data, it's occur in the both sides. So meaning we have red in the green side, we have green in the red side. So we can't really split it with a huge or wide margin, so which we could call as hard margin. So for instance, in this particular occasion or the situation, we can call it, we have soft margin instead of hard margin. Okay, in terms of mathematical representation in SVM, so particularly we are keen, or we are focusing on this particular equation, so whereby we have weight as W multiplied by the x is data point. This W, X, and B that we are having as equation over here is talking in the vector approaches, or as a data of the vector. It's not a numerical data. It's a vector data, meaning that we could have x1, x2, x3 in X, and while we do have bias b1, b2, b3 in B. Or same goes to the W weight. So that's the reason why over here we have W1 until WD as a vector weight, which determine the direction of hyperplane. So this is very crucial when we are having the maths exercise towards the end of this particular slides. B is a bias turn. Bias turn is basically added to this equation to shift the hyperplane away from the origin. So imagine that we have y equal mx normally. So the y mx is crossing the origin, isn't it? And say that if we add y mx plus c, so basically the y mx is not really passing through the origin anymore. So because we have plus c, so same goes to this way. We have plus b. It's basically bias makes the equation run away from that particular origin, which might be decreasing our SVM capability, or try to generalize the unseen data at the point of view of SVM, right? So the margin is computed as 2 over W, where W is a norm, or alias we can call it magnitude of the weight vector W. So this one is the vector weight. The factor 2 over here is basically means that the width of margin spanning both sides of the hyperplane. So the 2 means is basically this one, guys. If I could repeat again as it is. Oh, it's not here, but where is it? Oh, it's here. So meaning the combination of the two margin, the class number 1 to the hyperplane and the class number 2 to the hyperplane, combination of that one is 2 out over 1 over W in as a norm magnitude. Okay, right. So the margin itself, which happen to be crucial, is when we talk about when we try to change the hyperplane to find the most valuable hyperplane to that SVM that we chose. So example, we at the first point we have green. So take a look at this particular green. So we have this distance for support vector for the plus data, while this one is the support vector for minus data. So right, so this is the distance between those. But eventually, if we take the black line as our hyperplane, for instance, over here, this is the hyperplane. So we can take a look that two of these support vectors for the plus data is far enough from this particular line, green data, right? So this could be identified that the black line is having the maximum margin compared to the green line in this case, right? Then after we did understood about the hyperplane, the margin, so then we go to the support vectors. So as I mentioned earlier, so we have support vectors is basically the last particular point which close to the hyperplane for each either data sets of the blue one data point and data point of the red one, right? So the closest to the hyperplane is called support vectors. For the blue one is two data, while the red is only one data, which the closest one. So that would be the support vectors. Circles show the close data point to the hyperplane are support vectors. So basically, we indicate those three data points, in one from the red data, and the other two from the blue data with a circle, right? So the margin over here, P, is basically 2 over the W in magnitude. So that is what we call it separator, distance between support vectors to support vectors. So whereby we have 2 over W. Right. Which hyperplane produce maximum margin is our target for now. So in order to have that objective achieved in our hands, so basically we need to discuss about the support vector itself are critically data point that lie closest to the hyperplane that we have discussed earlier. So the moment that we wanted to maximize our margin, so the margin is determined the distance between the closest one, right? So basically we need to push up against the margin, so that the choices of us is influencing our maximization of the margin in order to have a good SVM. Yes, right. So then if the margin is maximum enough for our selected hyperplane, then this is ensuring the largest separation between the classes. So it makes the hyperplane will be generalized enough for every unseen data, and it minimizes the error of generalization, so making the model perform better for unseen data, or alias we can say good enough to a new data which has been brought by us to the same model. Okay, why the maximum margin is important? So yeah, a larger margin reduces the likelihood of overfit. So I think we did discuss about overfitting last week. So we have just fit, we have underfit, and we have overfit. So overfit is the same thing when we talk about machine learning in general. So because support vector machine is one type of the supervised learning, the same goes to classification and whatnot. So basically, if we reduce this particular margin to be extensively as a small margin, so most likely the model will be overfitting, and yeah. So in other way around, we need to have a large margin in hand in order to reduce this overfit. So at the end, we can say that the model is better enough to get a generalization impacting unseen data to be having a good classification or estimation percentage in terms of analysis. So adding new data is less likely to misclassify if we have a large margin with a hyperplane that maximum margin enough. So yeah. So on the left, the improper aligned hyperplane shows that minimal margin over here, while on the right hand side we have corrected the align hyperplane, maximize the margin. So this is in the blue region, right? Okay, I think so far up to here we have discussed about the some introduction of SVM itself, the definition of three things that we need to be understood beforehand, going up to the mathematical model and so on. So we did discuss about hyperplane, we did discuss about margin, we did discuss about vector, support vector, right? Yeah. So now I would like to show the several scenarios of SVM. I think this will be the scenario number 1. So here we have 3 hyperplanes. So imagine that we have A, B, and C. So now identify the right hyperplane to classify stars and circles data points. So we have 2 particular data over here. We have star and we have circle. So see, when we talk about A over here, this is the separation between 2 class based on that hyperplane A. So we can see over here stars and the red circle is included to each other, while this could be good enough in the sense of classification, while the choices of C is basically also mixed between stars and red lines. So at the end of the day, in this particular scenario, hyperplane B has excellently performed this job, right? So because of the stars is basically separated in star group, while the red line is separated in the same classes that lies in the red circle data, right? So we shall see the second scenario over here. So here we have 3 types of hyperplane A, B, C, and all are segregating the class well. So now, how can we identify the right hyperplane then? Yes. So we have B over here close enough to the stars, and C a bit in the middle way of B, stars and red circle, while the C is close enough to the red circle itself. So here we can say that maximizing the distance between nearest data alias support vectors for each particular class will help us to decide the right hyperplane. So the distance is called margin, as we did discuss before, right? So above we can see that the margin for C is the high as compared to the previous A and the B. So hence C is a good one. It's a hyperplane for this particular given data. So in this scenario, hyper C is excellently performed for this particular job. Right. So how about the scenario number 3, guys? Okay, right. So in this particular scenario, we have 2 selection of hyperplane. So we have A and also we have B. So some of you may have selected hyperplane B here, as it has higher margin compared to the A. So we can see over here the stars is quite far enough from the line, and also this. But eventually we have 1 star is jumping out of the hyperplane B, right? So but here SVM select the hyperplane which classify the classes accurately prior to maximize margin. B has a classification error because they have incorrect data which consider as A. So yeah, that's the reason why A is better enough to be selected for getting an excellent accuracy in SVM performance. Okay, right. Now we will jump to the scenario number 4. 1 star at other ends is like an outliers for star class, right? So outliers over here, I think we did discuss about the outliers deeply. I did take one of the male examples sitting, I think, in Friday class in the morning, right? So because that particular male student is sitting surrounding the female student, so that is particular outliers is considering the vision of female students, right? So for this case, the same goes for this case. We have stars in the red circle data, so that is outliers. So SVM has a feature to ignore outliers and find the hyperplane that has maximum margin. Hence, we can say that SVM is robust to outliers here. This is the best for selecting our hyperplane for discriminating the two classes stars and red circle. Okay, right. So in a next scenario 5, we have this X and Y. We have red triangle and blue circle. So in this scenario, we cannot have a linear hyperplane between the two classes. So whereby the class number 1 is the red triangle, the class number 2 is the blue circle. So how does SVM classify this particular two class? So till now, in our discussion from the page number 1, this particular slide, part number 2 SVM, we have only looked at the linear hyperplane, isn't it? Have you noticed that? So far, we just discussed on the straight line, and also straight line, right? It is clear that there is not a linear decision boundary for this particular straight line solution for this given data. So this is not particularly accurate for our discussion from now on, but may be accurate after this, right? Okay, so far, since we have improper data point that we have what we call it non-linear over here, so we might split it the type of data into two. So far we did discuss about the linearly separated data. Okay, so since the linear SVM is the first chapter for part number 2, so the training data can be separated by a straight line or straight hyperplane. Over here we can see the straight line over here. We have the diagonal line over here splitting the blue and the red datas. So the hyperplane maximize the margin between the class, work well with the data. It's simple and okay. As long as we have the hyperplane far away from each particular vector, support vector, so we might say that we have a good enough SVM hyperplane in this context. So from this two particular image above, so we can see that the two distinct clusters of this data can be separated by this straight line or linear separable data SVM case. So this is the linear case. So while this one, what we have is the things that we have in two slides before. This slide, right? So here we have case in non-linear SVM cases. Okay, it is not possible to separate the data with a single linear hyperplane, whereby imagine that we have this particular line over here run through here. So basically we could if say that, okay, so say that I put it here, so we can't really see that this could be a group or this could be a group, right? So eventually it's kind of difficult. Same goes to this. If say that I have line, okay, straight line is not possible to this, but this, right? So basically separating the this and that is basically hard to say, it's difficult. Okay, so meanwhile we can't really do that way. So on the other hand, we should have one particular trait or what particular skill in order to separate the data, so that the data is carefully separated to each other to make a good classification for non-linear separable data. So data is here what we can call still complex for a linear representation. So in the sense of linear discussion, so require a transformation. This is a keyword right here, guys, into a higher dimension space using kernel. Okay, right. Kernel is basically the thing that we will discuss later on about having one higher dimensional spaces, whereby if we talk about X and Y, so this is X and this is, hold on. If we talk about this is X and this is Y. So higher dimension spaces, basically we could add one more as Z. So that would be particularly going up to that discussion afterwards, I guess. Right? So this particular technique called as kernel methods like RBF and polynomial kernel transform the data to the effective classification. Okay, so I give you a hint over here. Basically, hold on. Imagine that we have y over here, we have x, we have z. Sorry. So the data is still the same. I mean, this one is triangle, 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 right? So at a certain point, basically the circle is going up enough to it looks like floating data in the Z form. So imagine that we see from this way, we will have X and Z, right? So the floating is basically here, and the rectangle triangle is basically downstairs. So then we can say that the kernel is basically goes here. Oops. Can I change the color, for instance? No. Okay. So then this particular line is basically a space in 3 dimension. So meaning like a piece of A4 paper is floating into the Z dimension. Okay. Right. That is kind of introduction of SVM, kernel tree. Right. So a bit about SVM, support vector machine calculation. So right, okay, here. So we will talk about the sum calculation, one example of linear SVM. So still in linear SVM, guys. Here we select two support vectors to start with. So basically we have this one is S1, 2, 1. S2 is 2 minus 1. And S3 is 4, 0. So basically support vector is the one that the most close to the hyperplane in the SVM discussion. So meaning this would be the closest point for either when we talk about what is this or that or this line. So this particularly will be close enough to that particular line. Okay, but the thing is, the line is still not fixed yet because I'll erase this one first. Because the idea is we need to find the hyperplane by maths calculation. So right, and to do this, basically we need to have some maths fundamentals and math knowledge over here. So here, how we do the maths at the beginning of find the linear SVM hyperplane. So here we will use the vector augmented with 1 as a bias input. So clearly we will differentiate for over tail. Okay, so the first thing first is we have the support vector to 1, 2, minus 1, and 4, 0 over here. So this is the data points that we have. So adding 1 is basically adding a bias to this each of S1, 2, and 3 for each data points as a support vector. So instead of having 2, 1, so we have 2, 1, 1, 2 minus 1, 1, and 4, 0. So by adding this one without a bias, the classify will always grow to the origin. So remember, the moment that I start this particular class, we said, example, y equal mx different with y equal mx plus c, right? So the moment we have c to the y mx is basically running away from the origin. So meaning, hold on, I sketch for you guys over here. So this is origin 0, 0. So the moment that we have 1, so basically the line could be this and it could be varies. It's not necessarily really will pass to the origin over here. So that would be the idea. So SVM does not give you the separating hyperplane with a maximum margin if it does not pass the true origin. Okay. So then to do this, we have a bias term. So this is the bias term that we have in each particular support vector. So yeah. So after we did fix the original support vector to S1 tile, so meaning over tile is basically this, guys. If where's my okay, so tile is meaning this S1 tile, S2 till, and S3 till, right? So now we need to find the parameter of alpha 1, 2, 3 based on the following three linear equations. So because of okay, right here the equation to say that the data belonging to one particular class is to multiply each of the data as a vector with the coefficient. So mean every single coefficient, example 1, 2, and 3 over here, will be divided like because we are talking about the 3 points, right? So imagine that the first case is S1. So data point S1. So every each of S1 will be calculated with itself and the second data point and the third data point, right? So basically the multiplication is like that for vectors. So same goes to the second point. So we have S1 2, S2 2, and S3 2. So basically this particularly focus on this S2. So while for S3 over here, obviously the class is positive class because positive in the right hand side, if we may consider it is as positive class, and the blue is negative because on the left. So S3, 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 and multiply with all other the coefficient and other data points, right? So okay, so after we did arrangement of coefficient multiplication between alpha, S1 till and S1 till and others. So basically we can put again the things that we fixed before as it is. So we did add this one at the beginning, right? So this one, S1 tile, S2 tile, S3 tile. So then what we do is bring that particular value here to put inside all this S, okay? We put here, we put here, we put there, we put here, and so on and so forth. So then we just remain the minus 1 as a class, remain as a class, and positive 1 as a class, right? So after we did that, so basically we did that, we just multiply them. So in example, I give to you for alpha number 3 or S1. So basically 4 times 2 is 8. And 0 times 1 is 0. 1 plus 1 times 1 is 1. So basically this is summation of 8 plus 0 plus 1 would be 9. So this 9 is basically multiply again with alpha 3. So this component will be known as this. As one part of example. So you might do the same as this, and this. So we have 9 components of alpha equal to minus 1, and plus 1, right? Okay. Towards the end, basically, in order to find the alpha value, so we need to have some maths in order to get the idea of alpha 1, alpha 2, and alpha t value. So to do that, basically, I'll provide you some particular maths solution over here. So the first, there will be, I think, 5 steps. Is it 1, 2, 3? Okay, 5 steps to go. Before we towards the end of the final value of alpha 1 and alpha 5. So for the step number 1 is eliminate alpha 1 between 1 and 2. So because this is the equation 1 and 2. So basically 1 and 2 means this and that. Okay. So the moment that we put alpha 1 and 2 over here, so we have in order to eliminate them, so as usual, we need to to eliminate alpha 1. So basically you need to have the similar coefficient for that particular alpha 1. So then we need to multiply equation number 1 with 2 by 3 instead of having 4 alpha minus 4 alpha is gone, right? So towards the end, we have -1 and this. Okay. So we have this. At the end, we have 10 over 3 alpha 2 plus 3 alpha 3 equal 1 over 3. Okay. Right. So then we have step number 2. So basically eliminate 1 for 3. So basically in order to do that, we need to have the same thing. So 3 by 2 is multiplied to 1. So basically we have this. And towards the end, we have this particular equation number 5, new one. So last time we have equation number 4, and this one is question number 5. Okay. Okay, step number 3 is solve alpha 2 and alpha 3. So using the equation number 4 we have in step number 1, and question number 5, step number 2. So we have this, and we multiply the number 5 with 10 over 9. So what we have is basically 10 over 3, and then 35 over 9, and so on and so forth. So then here we have we subtract then 4 by 5. So towards the end, basically we have A3 alpha 3 is 3.5 towards the end of subtracting 4 to 5, right? So then immediate after we have alpha 3 in hand, so basically we can find alpha 2, right? So we use equation number 5 over here because we have in our hand 3.5 as alpha 3. So in order to find alpha 2, we can use this equation. So now we put the numbers in here. So basically we have 12.25. So at the end of the day, alpha 2 is minus 3.25. We have here. Okay. So at the end, towards the end, in order to find alpha 1, so just use the alpha 2 and alpha 3 value to the equation number 1, just we have in the first point here. So because we have 2 here, we have 3 down there. So then at the end, we have 3.25 minus, same as the alpha number 2, right? So this is the idea of how we can calculate each of the coefficient of that particular support vectors S1, S2, and S3, which provided in that particular question. So there will be some other solution to be made, but the thing is I just provide you the normal associative laws by mathematical approach. So at the end, yes, we have alpha 1, alpha 2, and alpha 3. So towards the end, basically, in order to find the hyperplane, we cannot stop over here because this is just a coefficient, right? So not the truly line that we have. We need to solve the SVM at the first point. So right. So we need to find where is the line for these 3 support vectors, right? So to do that, we have a value for alpha 1, alpha 2, and alpha 3, right, in hands right now. So the idea is because the hyperplane vector is computed using the formula S, the vector is the summation of each coefficient to the support vectors. So meaning each of support vector. So I think we had seen this equation before. Over here. So yeah, this is the one. We multiply them and we sum them. So basically this is the one, right? So alpha 1 is a scale weight for each vector. Support vector is S, and at the end of the day, so n now is, what is the number of n, guys, as a quiz? Can you guess? For this one, so how many n been used? The total number of support vector. I think you can guess it. Yes. The n is now equal 3. Okay. So meaning I1, I2 and I3. So there will be three particular things. Yes, here. And then substitute the alpha 1 and alpha S1, alpha 2, and so on. So basically, we have this particular things. Minus 3.25211, minus 3.252, minus 11, 3.5, 4.0. So towards the end, basically, the weight vectors of the W here is 103, right? So this is the set of the vector that we have for W. So W means, remember, is imagine that we have y equal mx plus c. Okay, so W is basically m for that sense. So m is basically the slope, right? So the idea of explaining the slope, so we did add the last point of the vectors as bias, right? So meaning this is the bias. Okay, minus 3, not this one. So the first 2 points is basically explaining how the x and y are being characterization in the lines. So meaning here, 1 is dependent to the x-axis and y is the y-axis. So meaning only y-axis got coefficient in this sense. So while x have 1, but y-axis doesn't have any coefficient. So whereby here we can say that the line for 1, 0 is basically the straight line to the top, because the y is not having any. So that's the thing, is no correlation between y-axis. So because y-axis just 0. Okay, y-axis mean this axis, so meaning y, x only 1, right? Speaking of the tree, guys, tree is basically the jumping from the 1, 0. Okay, so basically the bias is from the original one. So this is the original. So 1, 2, and 3. So this is the minus 3. So meaning, yeah, this is 3. Okay. So the 3 is happen to be as a bit far away from origin. So that's what we have in this particular 1, 0, and minus 3. Or hyperplane line dedicated to the example number 1, or linear support vector machine, right? So this is the one. So say that we want to confirm either our selected line is on the board or out of the case. So say that we take 3, 1. So where is the 3, 1, guys? Hold on. 3, 1 is basically here. 3 and 1 over here, right? 3, 1. Say that this is the data that we choose over here. Okay. So 3, 1 is the, what is the 3, 1, guys? Say that we have 3, 1 here. Either W, X, or B. Which one is 3, 1? Yeah, 3, 1 is X, data point. Okay. So the W is, we know what we have just now is 1, 0. This is W. While the B here is the bias. By bias, we have this, minus 3. Right. So we put all the value into this W and B over here. So we multiply with 3, 1. So 3, 1, let's say here 1 times 3 is 3, 0 times 1 is 0. So 3 plus 0 is 3, 3 minus 3 is 0. So the definition says 0 is true for the data which on the line of hyperplane. So that's the way. So if we have the other value for 0, so meaning that the data is on this side or that side. So either way, right? So since that we have 0 in our hand for 3, 1, so meaning our answer is good enough for describing the hyperplane for this particular 3 support vector data. Alright, jumping to example number 2. So we have this data point. Yeah. So this one, example, we have this particular tree, if I may. Okay. So because of the tree, so basically we can say that we have S1, S2, S3 over here. So S1 is 1, 0, S3 is 3, 1, and 3 minus 1, right? So then we add the, what we call it, bias over here. So the same idea we goes to calculate all the till S1 until S3 with each as a vector calculation, right? So remember that the left hand side is -1, right hand side is +1. It depends on what you said it. At the end of the day, basically we have the same the idea of this data, right? And we try to put back again. So finally we have this 1, 0, and 2 bias. So 1, 0, and 2 bias, as I mentioned earlier, is a straight line from the x2, because -2 over here means away from the origin, right? Okay. So then draw and calculate the hyperplane for this particular example number 3. S11 and 22. So this one is right, is kind of tricky. It's not a straight line from x axis or y axis anymore. So we have 1, we add the bias and we add the bias. So what we have over here, we do the same, and particularly we have this equation or coefficient that we have. So at the end of the day, so the idea of x, y, we have this. Okay, so 1, 1. So this one is rated to x and this one rated to y, right? So this one is the bias. Okay. So meanwhile, 1, 1 meaning away from x1, away from y1. So then what we have is here. So this is 3. So this is the line explaining the idea of 1, 1 minus 3, right? Okay, so this is some exercise for you guys to do at home. So I hope that you can do it by your own here. So you are trained SVM and tiny dataset with 4 points shown in the figure below. So the data consists of 2 examples and so on. I'll find out the W and B and finally draw the hyperplane. So this is the, I think, more or less to be as your homework for this particular coming lecture session. Also, right, okay. So we did mention about SVM got 2 particular things. One is linear and the other one is non-linear, right? Okay. So the non-linear, I think we did discuss, I did show to you guys this particular graph. Hold on. Okay, so we have here x and y. So because the data cannot be split by a single line or a straight line. So what we'll do is basically we try to add one third dimension. Instead of x and y, we add z on the other hand, right? So we create a z dimension and we rule the calculation a certain way that is convenient for us. So we may choose z equal x squared plus y squared, whatever it is, which very helpful to us. So towards the end, basically this is the z, how we see the z from x, right? From, I think I did sketch it over here. Oh, it's too far. I think you can place back the slide before. Okay. So now after we split it, so we can see that the majority of the triangle data is floating away from the x-axis, while the blue is basically surrounding the origin, so 0, 0 location. So then we can slice them by the x domain to split the upstairs and downstairs. So this is the best hyperplane in 2 directions. Okay, so I think that is the idea of nonlinear SVM. So here we can call this particular thing as a kernel trick. So I think we do have some discussion on that. So note that since we have the 3 dimension, the hyperplane is a plane parallel to the x at certain z equal 1. So basically this is the nonlinear separation or hyperplane that we have for SVM. Okay, so there are functions which takes low dimension into space to the higher space is convert not separable problem to the separable problem. This function are called kernel. So this is the way that I did mention earlier about the kernel trick just now. So it's mostly useful in non-linear separation problems. So because in the sense of data that we have in perspective of nonlinear, so for example, human facial, what else? The discarded data that we have in nature, or pedestrian way that step taken, for example, okay, it's not cat and dog issues, okay. So in a higher dimension, it's very likely that the linear separation can be constructed. So because when we change the 2 dimension into the 3 dimension, we can slice them, right? Constructing a separating hyperplane with maximum margin in the higher dimension space yield a non-linear decision. So this is the keyword for kernel trick. Okay, right. So this is the one that the kernel approach, a simpler, efficient computation approach to the non-linear boundary between classes. So the kernel can be any degree, either shape, polynomial, round, or what else that we have. So this function maps the non-linear separable into space into higher dimension linear separable features. So for example, this is the things that we did saw just now, 2-dimensional x and y. So if we put one other higher dimension in this particular slide, for example, z equal x squared plus y squared, we can see that some data is floating away upstairs and some data will floating also by the downstairs. So we can slice them by the having the 3-dimensional hyperplane disk. Okay, seems to be like a piece of paper, A4 paper on the dimension. So we might have several points of a kernel. So we do have polynomial over here. We do have a radial basis function, as we mentioned at the beginning of the slides. We have sigmoid, right? So I think to discuss about multi-class SVM, so I basically multi-class support vector machine. So in support vector machine, it's not a multi-class type of machine learning, but happen to be more directly to discuss about 2-class classifier. So however, to do a multiple class type machine learning, so the SVM can combine a number of binary classifier uses using some strategies. So one is 1 versus all, and the other one is 1 versus 1. So this is the things that we have two. It's not 2, but 2 is black and red, but we have another one blue. So meaning, so now we have 3 classes scenario of having SVM. So how the SVM deal with multi-classes SVM? So basically we will discuss in our next class. So I think that's all for today. See you when I see you, and take care. Bye.